All right, everyone doing okay? Our test is a week from today. So we're going to finish up partial fractions. We're going to talk about the test next class, and then you'll have the weekend to prepare, and then we come and take a test, right? See where we are. I was asked a little bit about number 11 in the homework, so here it is worked out. I will just go through this real quick just to point out some of the key factors here. We had an integral, and the denominator was quadratic, but that quadratic could be factored. And so if you factor it, you get two linear factors. And so last class we learned that if you have distinct linear factors, you could break that up into this format over here, right? And then I went through and did the work and figured out what A and B were, and then come back in here, and then I just have to integrate these two. And it's pretty direct because it's just going to be like 1 over u's on both of those. And we're going to be doing a little bit more of that today. I also want to point out from last class, just to remind you, that when we started off the class, we had this example here where we had a quadratic, and above it we had a linear expression. And it was really what we were trying to see, or what we saw here, is that if you look at the bottom and make a basic substitution, use the bottom, then the derivative was right there on top, right? Remember that one? We were real happy about that because it was a real quick answer here. And then I believe after that, I showed you this example where we had a quadratic on the bottom, we had a linear expression up top, but it did not match, right? You take the derivative of the bottom, it was not 2x minus 3, so I was clever and I came in here and I rewrote the plus 1 as a minus 3 plus 3 plus 1. Do y'all remember this example? And what happens here is that we can break it up into two integrals. One of them should be pretty straightforward. It's just 1 over u du. The other one, what did we do here? We completed the square, okay? Now, so if we can get a quadratic, and this didn't factor, did it? Right? Remember, that was one of the keys, is that this didn't factor down here. But if we could get a quadratic down here and then we could get its derivative up there somehow, we might have to split it apart and do completing the square, but we should be able to handle it. Agreed? Okay. We need that going into the rest of today's, to remember what it is we can handle at this point. So let's go ahead and begin. Today we're going to go and look at, I should go back. We had different cases. Where did my cases start? I know I wrote them down. Okay, here we go. We had case 1 where we had distinct linear factors. We did that. We had case 2 where we had repeated linear factors. We did that. And we even had to break out the calculator. Well, we didn't have to, but I showed you how to use a calculator to solve systems of equations. We had not done case 3. So let's just remember, case 3 is where we have irreducible quadratic factors. That means we have a quadratic factor somewhere down here that cannot be factored. Irreducible means not factorable. So here's an example of a quadratic that can't be factored. Here's another example of a quadratic that can't be factored. So in the event that we run into those, what they suggest we do is rewrite each quadratic factor with a linear expression on top. Why do you think putting quadratic with a linear on top is going to be useful to us? Yeah, like what I just showed you a second ago, right? When we had a quadratic on the bottom and linear on top, if we could get things to work out properly, we could handle it. So that's what we're shooting for. So do you understand that the scope of the magnitude of each of these problems is actually what we did before? So we're going to be using partial fractions just to get us to what we had last class. And then from there, we will have to break it out and complete square and do all that junk. So let's get going. Here it is. So I'd like to start with when is it that you use long division? Just so we're all clear. When do we use long division? when the numerator's degree is higher, right? Or equal, right? Or equal. Or you could say you don't do long division if the denominator's degree is higher than the numerator. But if they're the same, you use long division. If the bottom's smaller than the top, you do long division. So just make sure you're clear on that. There was one problem I know could have been done fairly easy if you did the long division first. If not, it became somewhat of a nightmare. But still, it could be done, right? The one that y'all did, it still worked out without the long division, just a lot longer. Okay, so here we go. Right now, we do not want to look at long division. I think we can throw all the other techniques out the window, don't you think? Okay. I don't want to use long division, or I can't use long division, so my hope is to try and break down that denominator, factor it, so I can see what type of factors I have down there. Are they linear factors? Are they, repeated linear factors, quadratic factors? What do we got? Everyone sees what we can do on the bottom to factor? Take out an x, and we're left with x squared plus 4. So what I have here is I have a linear factor in x, right? That's a linear factor. But x squared plus 4 is a quadratic factor. It's irreducible. I can't factor x squared plus 4. I could factor x squared minus 4, right? But not plus 4. So I have one distinct linear factor and one irreducible quadratic factor. That's what I've got here. So I'm going to start my partial fraction decomposition. I'll come back to the integral in a second. What I need to try and do is take this expression, and for each linear factor, I put what? A over that linear factor, but I only have one of them, so I'm just going to put that. And then for the quadratic factor, I need to put a linear expression on top. So I can't use A, I need to move to the next letter, so bx plus c. If we use c now, just remember at the very end, c is going to be different, our plus our constant. All right, and then all over this. So now what we need to do is we need to get a common denominator, right? So I multiply everything by this. On the left side, I'm left with just the 2x squared minus x plus 4. On the right side, I'm left with what? A times x squared plus 4, and then plus, I have to multiply bx plus c by what? X, right? So is it all right if I put bx squared plus cx? Everyone with me? Now, I did show you that shortcut where you sit there and you say, let x be something, right? Does everyone realize we're never going to be able to kill a? We can't kill a because there's no way you can make that 0. Which is why I showed you that the other method is more powerful. The shortcut's cute, but it's not as good as just doing what we did last time, setting up a system of equations. So I'm going to just distribute my a through. I've got 2x squared minus x plus 4 must be equal to ax squared plus 4a plus bx squared plus cx. And then what did we do after we kind of expanded everything out? Just like terms together. So we have 2x squared minus x plus 4 must be equal to, so can I do a plus b x squared and then plus cx and then plus 4a. And now we match up coefficients. So I know that the thing in front of x squared, right, 2, must match up with a plus b. Ooh, this is going to be nice. -1 which is the number in front of x, must match up with c. That I know what c is then, right? C is -1. Also, I know that the +4 must match up with this constant over here, which means I know what a is, don't I? So I'm going to write those three equations down. I have a plus b must be 2. I have that c must be -1, and I have 4a must be 4. Now, I wrote it like this because I actually do have a system of equations here, right? So we could do the matrix on the calculator and stuff, but why do that? You already know what two of your variables are. If you know what two of them, you should be able to get all of them. So just by looking at this, I know that a is 1, right? C is -1, and then to get b, I just have to take this right here, replace a with 1, and so b is what? B is 1. So I know a, b, and c. I'm in business. Questions? We're not done, right? Okay, now we got to go back and rewrite the integral. Remembering that we're going to rewrite this integral as a, which will be 1, right? 1 over x. Then it'll be x plus, or actually x minus 1 over this. Can I go to the next page? Okay. All right, so I have integral 1 over x plus x minus 1 over x squared plus 1 dx. That's what the partial fraction decomposition allowed us to do. Yes? Did I miss something here? Oh, did I put 1? Oh. What are you talking about? Is it 4? I am glad you mentioned that, because that would have caused a problem later. How about that first integral, 1 over x? Do that in your sleep, right? This, however, the first thing I'm just going to look at is if I call u the bottom, what's the derivative of the bottom? 2x. I have x, so it's not exactly matching up, and I've got this minus 1. Does anyone see what I can do with this, though? Well, this is already completed. Look, if you look at completing the square, this is already completed, right? It's something squared plus a number. Any ideas? The x squared plus 4 should be making you think arctan right now, yes. But arctan will only work if that's a number up here. I've got that x up here. I'm just going to put a check mark next to that I have that one. So over here, I'm looking at this now. So wait a minute. If I call u the bottom, what's the derivative of the bottom? 2x. If it was just x up there, would you be able to handle that then? Okay. And now if I didn't have the x up here and it was the number, you said you would use arctan. But isn't this minus this, you can split this into two separate integrals then? So let's just do that. Let's just make that equal to x over x squared plus 4 dx. And then I'll put, how about minus, because that's a -1, 1 over x squared plus 4 dx. Did you agree that's the same thing? The first one, how am I going to handle the first one now? Basic u substitution, right? Basic u substitution. I see something in its derivative. I'm off by a constant. This one over here, arctan. Yeah? Quick u sub on this. Use x squared plus 4 du is dx, not dx, 2x dx, which means 1/2 du is x dx. So that integral becomes 1/2 integral 1 over u du. Everyone follow my quick u sub here? And then the antiderivative here would be what? Natural log of u, but what's u? X squared plus 4. So I've done all this. This integral is complete. Over here, it's arctan, right? But what's a for us here? A is 2, right? A is 2 in the formula, and the antiderivative of x squared 1 over x squared plus a squared should be 1 over a arctan x over a. That's in your formula sheet, right? So this whole thing just becomes minus 1 over a arctan of x over a, right? Y'all still following me? Now this, remember, was just this part, which was just this, right? So I'm ready to put it all together into a final answer. Any questions, though? So our answer is, remember the one we checked off here was what? Natural log x plus, now down here we had 1/2 natural log x squared plus 4, and then we have minus 1/2 arctan of x over 2 plus c. So the problem started out, the only thing that we didn't have in this problem that would maybe be one additional step would be if you had to do long division first. And then after long division, you got this. And then you do your partial fractions, then you split that up, and then you do, you know, everything we need. Also, as you're going to see in the next example, this worked out real nice here, didn't it? Basic U substitution, arctan immediately. On the next example, when we get to this, it's not going to be that. We're going to have to complete the square. Do you have any questions, though? All right. Here we go. Next example. Integral. By the way, I'm just doing the examples in the book. They're pretty good, so I wanted to just go and use those. A lot of times I don't like to use the examples in the book because I want to give you something other than that, so you can look back on that as another reference. But students, for some reason, have trouble following the book sometimes. So, have y'all tried looking at the examples in the book and seeing how they're worked through? Has that helped? Good? Has it been good or bad experience? No, haven't tried it. I think reading a math book is a skill that takes time to develop that, but you got to try at least. All right. So, long division, same powers, right? So I'm going to do the long division over here. Now, I'm actually not going to go through the whole long division, all right? Unless y'all really want to see it. Vote. How many of you want to see it? Don't feel bad? 2? Yeah, is that, I mean, I don't mind doing it. It's just less examples I get to show you the more work I show. Y'all have to respond. Y'all have to let me know. I mean, yes or no? No? So the yeses, there's only 2, 3 yeses? How many no's? Okay, the no's are going to take it. You got to vote. Okay, so if you do this, all you're going to get is 1 plus, and then your remainder is going to be x minus 1 over the divisor. 4x squared minus 4x plus 3. All right, so now this integral becomes two integrals. It's 1 dx plus integral x minus 1 over 4x squared minus 4x plus 3 dx. Right. Please pay attention to what I'm about to tell you and show you. Should I go and, well, now you tell me, what should I try right now? Try to factor this, right? How could you tell that's not going to factor? Right? What's a way you can always determine if a quadratic factors or not? Do you remember me talking about the discriminant last time? Quadratic formula, there's this thing in the quadratic formula, b squared minus 4ac. Do you remember that part? It's usually underneath the square root. That's called the discriminant. What's the discriminant here? So what's b squared? 16 minus 4 times 3. That is a negative number. If your discriminant is negative, it's not going to factor over the real numbers. If your discriminant is 0, it will factor. If the discriminant is positive, it will factor. Now, you may never be able to factor it, but it's factorable. If it's negative, it's just never going to factor. Okay? So this is definitely an irreducible quadratic. Since it is irreducible, it's case 3. But what does case 3 say? Case 3 says every time we have an irreducible quadratic, we want to rewrite this thing as what over that irreducible quadratic? In this case, it would be ax plus b, wouldn't it? Yes? Since there's only one factor, that's what I should use over there. In the previous problem, we had a linear factor along with the irreducible, didn't we? A linear with the irreducible. In this problem, we just have the irreducible. And our goal is to try with partial fractions to rewrite it so it's ax plus b. Should I go do that? This is a question to you. Should I try and write this as ax plus b over 4x squared minus 4x plus 3? Should I go try and do that, yes or no? Why not? It's not going to help. Don't I already have that? Don't I already have ax plus b right there? Right? I mean, I already have this here. So going through this partial fraction, my goal is to, if your goal is to get that, you're there. Right? You're there. Y'all see that? You do not want to waste your time on that and on a test. So now we're stuck with, well, what do we do then? I mean, what was the whole idea behind that? Well, the idea was that if you can get a quadratic on the bottom and a linear on top, then you should be able to do something to grind it out. Most likely you're going to need completing of the square at some point. But this is where I deviate a little bit from the book's approach. All right, so if you read through the example in the book, the way they do it is a little different than the way I'm going to show you. And this is just the way that I've, I guess, learned to enjoy these, all right? So I'm going to take that and do it on a different page. Remember, we have an antiderivative over here. The answer is x, right? And we'll come back to it later. So I'm trying to integrate x minus 1 over 4x squared minus 4x plus 3. Now, we said last class that it would be just absolutely great if the numerator was the derivative of the bottom, right? So if I were able to make the substitution, u is 4x squared minus 4x plus 3, what I would need up top would be what? 8x minus 4. I do not have 8x minus 4, do I? And I can't do that thing that we did last time. Remember where I added and subtracted that number to try and make it match? Because That worked because this was already, I think it was a 2x, and what was down here was x squared. But I'm actually going to force an 8x minus 4 out of this right now. Okay? You ready? Here it comes. I'm going to start with the x. I need the x to be an 8x, right? So I'm going to multiply the top by 8 and the bottom by 8. Agreed? So this now becomes a new integral. I'm going to leave the 8 in the denominator on the outside, but I'm going to pass the 8 in the numerator through. And I get what? 8x minus 1 all over 4x squared minus 4x plus 3 dx. Y'all agree with that? No, that's not right. That's an 8. Okay? Right? We okay with that? So I've now forced my x term to be exactly what I need. But now I need a minus 4 plus 4, don't I? I mean, not the minus. I need a minus 4. So how am I going to get a minus 4 out of this? We can subtract and add it, right? So now I rewrite the problem. 8x. I subtract 4. I'll put it in a different color so you realize I did something here. Subtract and add 4, but I still had what there? Minus 8. And then over 4x squared minus 4x plus 3. It is very important that if you're going to use this approach, you go after the x term first, like I did with the 8 on the outside, 8 over 8. You got to do that first before you add and subtract the numbers, or else things are going to get all messed up. So I haven't changed the problem, have I? I've just kind of manipulated it. So now if I look at this and I split this right here, this left side, 8x minus 4 over this, is just 1 over u du, isn't it? It's exactly what I need over there. Now this one's going to become a negative 4, isn't it? And then that's going to be a number over a quadratic. And when you have a number over a quadratic, we can do completing of the square. Okay? So rewriting this, this is 1/8 integral 8x minus 4 over 4x squared minus 4x plus 3 dx. And now this right here, what did we say it's going to turn into? Negative 4 over this, but that negative 4 can come out, can it? And join that 1/8 that's out here. So can I put instead minus 1/2 integral 1 over 4x squared minus 4x plus 3. Are y'all okay with me doing that? That negative 4 right here came out. Negative 4 over 8 is negative 1/2. That's outside the integral now. I left a 1 out there when I did that. And that's the denominator. Any questions? Should I put a check right here? Yep, that's 1 over u du. We should be able to handle that. In fact, it'll be, what? 1/8 ln of this, right? And we're done? Okay. We'll come back and put the final answer together at the very end. But now I need to come over here and I need to complete the square on this. To complete the square, you must have a 1 on your x squared term. So I'm going to pull this 4 out. That means I'm going to pull it out here, which means I'm going to pull it out of the integral. You okay with that? Okay. And this right here, check, check, check. We're going to worry about that later. I have negative 1/2, which is going to become a negative 1/8 integral 1 over. Now, if I factor the 4 out of the bottom, that means it's going to be x squared minus x plus 3/4 dx. And now we can complete the square. So to complete the square here, I take the number that's in front of x in the middle here, which is a negative 1. I divide it by 2, always. I square it, that gives me 1/4. I'm going to add and subtract 1/4, right? So my new integral is negative 1/8 integral 1 over x squared minus x. I'm going to add my 1/4. I'm going to subtract my 1/4. And then I still had down there plus 3/4 dx. So that's my completing the square step. The first three terms are guaranteed to factor, perfect square trinomial, right? And it'll always be in parentheses x and then this number. So minus 1/2. X minus 1/2 squared. And then the last two numbers, when we put those together, we get 1/2. So plus 1/2 dx. And if we look at this and kind of squint our eyes a little bit, we have 1 over u squared plus a squared, arctan, right? 1 over u squared plus a squared. For us here, a is what? It's 1 over 2, but square root, right? So it's just 1 over root 2, which we said last class we don't care to rationalize it. We just leave it like that. Got it? All right, so I'm actually going to do this because I'm going to use the formula. This equals negative 1/8. That was out there. Now my formula for arctan. 1 over a, which for us would be root 2, arctangent of u, which for us is x minus 1/2, over a, which is 1 over root 2. Questions? Put it all together. Here we go. Final answer to the original problem, which I wrote in black, so I'll come back here. Oh, I can fit it right in here. So this is now going to be equal to antiderivative 1, which was x, plus, was it plus or minus? The 1/8? That first integral? It's 1/8 natural log 4x squared minus 4x plus 3. That's what we got from this one, right? That we checked right here. And now this one comes down to be this right here. So I'm going to have negative root 2 over 8 arctangent of what? X minus 1/2 over 1 over root 2, which I could clean this up, couldn't I? A little bit inside there. Like 1 over root 2 is the same as multiplying through right here by root 2. But that's acceptable as an answer for me on a test. And that's it. Now I want to show you what the book has as an answer so you can see some comparisons. They did it a different approach, but can barely read this book. 1/8. So the book matches us exactly there, but then they have minus 1 over 4 root 2 arctan of 2x minus 1 over root 2 plus c. So if you looked at this, you might think that you're wrong, perhaps, but this right here is this, right? If all I'd have to do is multiply root 2 on the top and bottom here, right? If I did that, I would get root 2, that's 2. 2 times 4 is 8, and then on top you'd have root 2. So those are the same. And then to see this, It might be easiest to see this by taking ours and rewriting this bottom as root 2 over 2, and then reciprocate it up, and the 2 comes up through here and multiplies through and gives you this. They're the same answer is what I'm getting at, all right? I'm going to erase that, though. I don't want that as part of my answer. Okay. What do you think? Time consuming, yeah, it is. But you can see that if we can get it to be quadratic on the bottom and a number on top, we're most likely going to complete the square. If we get a quadratic with linear on top, that's even worse because we're going to have to split it up. And one of them will be completing the square. The other one's going to be probably a natural log. What if we get a quadratic on the bottom and a quadratic on the top? Long division. So we can basically take all possibilities here and reduce it down to one of those two. Quadratic linear, quadratic constant sort of situation. Very good. So what would happen with case 4? Case 4 is where we have repeated irreducible quadratic factors. Repeated irreducible quadratic factors. If I have my notes from last class here, here's an irreducible quadratic factor. And then here is the attack for it. So you try and get this, because it's to the third power, you have to do the quadratic factors to the first power with the linear on top, then quadratic squared, linear on top, quadratic cubed. So we just keep bringing the power up. This would be actually a pretty nasty situation because for this we already know the amount of work involved, right? And then these would be even more of the same sort of work. So it really is not a good situation to be in. So let me give you an example of one of those types of problems. Was I back to today? Yeah. So let's say we have integral 1 minus x plus 2x squared minus x cubed over x times x squared plus 1 squared. So what are you thinking here? Degree of the numerator? 3, right? Degree of the denominator? 5, right? Because you got x squared plus 1, you're going to square it. That would give you an x to the 4th term. Then you have an x out here, so x to the 5th. So we do not need long division, right? If we did need long division, what would we have to do? We'd have to like expand all this out and then line everything up and then do our long division. Okay. There is a possibility here that the numerator factors and that something cancels, but I don't see it. I don't see that possibility. I don't see it happening. So we're going to just go for a brunt force attack on this. Brute force. Brunt force? What the hell is brunt? The end, yeah. You get what I'm saying. All right. We have in the denominator what? What's that? Linear factor. So for that I put a over x. And then here we have irreducible, repeated quadratic factor, right? This is irreducible quadratic. It's repeated because it's squared. So what I'll need to put here for it is a linear expression, bx plus c over that irreducible, plus what? Dx plus e over the quadratic squared. A, B, C, D, E. We have 5 unknowns. Now what we do is we multiply both sides by the LCD. Okay, so when I multiply the LCD times this first term over here, only the x goes away, which leaves me with both of those factors, right? So my left side, 1 minus x plus 2x squared minus x cubed must be equal to the a times the x squared plus 1 squared, and then plus. Now, when I do this right here, this x squared plus 1, there's only one of them, right? So when it hits this thing, the x is still there, right? And one of those is still there. And we had the whole thing there itself. So I have bx plus c. I have the x that didn't go away, and I have an x squared plus 1. And then the last one, that dx plus e, the only thing left there after I hit this with the LCD is what? X. And now you can try to play that game of, okay, let me try and kill off things, but you won't ever be able to kill this one off, right? Can't kill off A. So I'm going to just go to the other approach, which is just multiply all this out. Line up coefficients and go from there. Solve my system of equations. I'm also going to take this time to rearrange the other side, put it in descending order. You don't have to do this, but kind of follows along with what we've been doing. All right, I'm going to try and do this in my head. X squared plus 1, when I square it, it becomes x to the 4th plus 2x squared plus 1, right? Because you have to FOIL and collect. Then you multiply times a. So I'll have a x to the 4th plus 2a x squared plus a. Y'all agree? Then this one right here, I'm going to multiply this. I think what I'll do to help me out is I'll just distribute that x through real quick. This is x cubed plus x, right? That's just that x right in here. And now I'll just do my FOIL on that. So I'll have bx to the 4th plus bx squared plus cx cubed plus cx. Notice I'm writing a little bit smaller and a little bit tighter right now because I realize how much I'm going to have out here. And then the last one will be dx squared plus ex. Let me collect all my stuff together here. How about my x to the 4th? Got one here. Got one right there. That's it. A and B. It's a plus b, x to the 4th. Now let me look at my x cubes. Ooh, I just have one of them. Okay. So I have plus cx cubed. And then I look for my x squareds. I've got a 2ax squared, a bx squared, and a dx squared. So that's going to be, in parentheses, 2a plus b plus d x squared. Running out of colors. How about my x terms? I've got a cx and an ex. So C plus E X, and then how about constants? Just A plus A. So I think what I'll do now, any questions on this? I've got to match stuff up, right? So I'm going to have a system of equations. The first equation, A plus B must be what? We don't have an x to the fourth, do we? Right? There's no x to the fourth out there? Maybe I shouldn't have an arrow then. Okay, that has to be 0 because I don't have an x to the fourth term over there. So A plus B must be 0. Watch the way I'm going to write that. And then the next equation, my C must match the number in front over here. So C is what? -1. D, I mean not D, the next equation, 2A plus B plus D, 2A plus B plus D must be negative, what? Negative 2, right? So I'm matching this with the coefficient over here. And then C plus E must be 1. And then A must be -1. Thank you. And A must be what? 1. Now you could do this as a matrix, right, on your calculator. You're not going to need to, but let me just jot this down real quick. Your matrix would come out, you'd have 1 1 0 0 0 and then 0. Then you would have 0 0 1 0 0 -1. Then you'd have 2 1 0 1 0 2 0 0 1 0 1 -1, and then 1 0 0 0 0 1. Now I'm just showing you that because that's the way the matrix would be set up. If it weren't so easy to solve, which this one is, then we would probably need to go to the matrix to get it, right? And do your RREF on your calculator. That'd be a lot to type in, but trust me, if this wasn't easy to solve, you'd want that, right? All right, let's try and negotiate this here. I know right off the bat A is 1, okay, from that. And then if I go up and use that right here, if A is 1, then B is what? -1. Oh, I know what C is. C is -1. I think the next easiest one to get is probably this one, right? If I know C is -1, then I know that E is 0, right? And then this one right here, 2 times A, but A is 1, so 2, take away 1, which is 1. Move it to the other side, so D is 1. Do y'all feel comfortable that y'all could get those all? And now I just need to go back and rewrite the integral right here. Right? It's going to be this. Are we ready? Our integral becomes, help me out because I can't flip back in my, 1 over x plus -x minus 1 again over x squared plus 1, and then plus x over x squared plus 1 squared. That's it. Was the D 0 or the E was 0? The E was 0. That's why we don't have anything out here. Okay. Yes. Yes. We okay? So now this is equal to natural log x plus, now I'm going to make it a minus. I'm going to go integral x over x squared plus 1. Why am I doing that? Because if I split this up, right, I'm going to have x over x squared plus 1. That's a basic substitution. U is x squared plus 1. The derivative is 2x. I'm off by a constant, right? So I'll be able to handle that. And then if I do this one over that, minus integral 1 over x squared plus 1, that will be what? Arctangent. And then plus integral x over x squared plus 1, but this one's squared. How am I going to do that one? Another u substitution. U is x squared, du is up here. We're off by a constant. Without me showing you the actual u substitution on those, I believe we should get a 1/2 natural log x squared plus 1 here. Then on this next one, minus, this is arctan, right, with a being 1. So when a is 1, it's real nice, just arctan x. And then this last one, when you do your u sub here, your integral should come out to be 1/2 integral 1 over, but instead of u squared du. And so that's the same as 1/2 integral u to the negative 2 du. The antiderivative of that is what? Negative 1. Careful, we're adding 1, right? Power rule, you add 1 to negative 2. Careful, you're adding 1 to negative 2, which will give you negative 1, right? So it's just negative 1/2 u to the negative 1, which is just, yeah, 1 over u. So this is negative 1 over 2u. So this becomes, I'll switch it here, negative 1 over 2 times u, but u is x squared plus 1. I would just encourage you on your own to, just finish this one up. If you need to, do the u substitution and do those. You should get this. Plus a constant. That's it. That's what it's all about. Okay? So these problems are taking us about 20 minutes or so a piece. $20. No, I don't know. I was telling you last class, that's the challenge for me, is to give you an appropriate variety of questions without making the test too long. One of the things that this test will indicate is not only your ability, but your comfort with the integrals, because if you're comfortable with them, it usually goes faster. And as far as like, okay, you identify the technique, you go after it. If you're going to take the first 5 minutes of each problem to determine the technique, multiply that times 8 problems, something like that, you've already eaten up a good 40 minutes of the test just with identification. So the time it takes you to take the test is part of the test, is what I'm getting at. What would you rather see? Let me ask you as a class. Would you rather see 4 integrals and give you, just, there's 4 integrals, but they're each worth 25 points, and when it's wrong, you pretty much are going to be, 2 letter grades? Or would you rather have more problems, And that depends on how much work you would show, so. You see the dilemma. Yeah, you can see that in this problem, there's so many different things you had to know that this is more of the type of problem you would see. Like, it's very unlikely that you're going to see, integral 1 over 4 plus x squared, right? I mean, as its own problem. So you can kind of eliminate some of the basic stuff, as far as, but I will try and, I am going to address every technique of integration on the test. I'm going to try to. You could. Yeah, there's nothing that says you can't. It won't pop up very often, but it could. All right, I'm just going to pick a random one here that looks pretty bad, and then I'm going to go for it. All right, so here we go. Now I'm working out of the even problems. I enjoy things like this. I haven't worked this problem out on my own, so we'll see what happens, right? What do you see? Long division, good. So we'll start with long division. Up top, I have x to the 5th. I don't have an x to the 4th, so I'm going to put a 0x to the 4th there. Shoot, I don't have an x cubed. I don't have an x squared. I have an x, and I have a -1. So I'm putting 0, 0 to align, to make sure I have spaces so I can line things up. I put x cubed out here, +1, and then I ask myself, what do I multiply x cubed by to get x to the 5th? X squared, so I'll put that out here, x squared. You don't have to put the x squared above the x squared. That's just one of those things I've seen some instructors do. So I've started doing it so that students are like, hey, why didn't you line it up? Well, there, I lined it up for you. So x squared. Now I multiply x squared times x to the 3rd, you get x to the 5th. Multiply x squared times 1, you get x squared. Come through and subtract, right? So what are we left with? Negative x squared plus x minus 1. Can I keep going? No, power here is less than here. I'm done. This is my remainder. So I'm going to, my new integral is going to be x squared plus the remainder over the divisor. The first integral is a check mark, right? 1/3 x cubed. We'll be fine with that. Here, did we start this class with power rule? Remember I talked in the beginning about how quickly this class, I mean, that now is, do we think about that anymore? Okay, that's a new problem. I'll come back up here later. I'm trying to do the integral. My instinct right now, I don't like the negative on the x squared. Personally, could I factor a negative out of the top and just pull out the, do you care if I do that? Or that's just my personal thing there. You wouldn't have to do that, right? But it's not incorrect. Just make sure you change all the signs. All right, here's what I'm now working on. Don't let me forget that -1 later. I need to see if there's a way I can break down the x cubed plus 1. Yes, sum of cubes formula. There's a formula for it. It is, let's see, x squared minus x plus 1. Down here, x plus 1 times x minus x plus 1. I'm using the difference of squares formula. Oh man, this problem's too easy. You see what happens? Oh man. I thought we were going to have to work harder than this. But hey, that's good. It's number 30. Do you see what happens? Because this factor matches that. But damn, what if I wouldn't have pulled that negative out? May not have been obvious, huh? I got lucky there. I think I still would have seen it. Would you have seen it though? That these are the same, they would have been off by a sign, so you pull a negative out. So when those go away, it's just 1 over x plus 1, the antiderivative is natural log. So we're kind of in good shape here, right? That was a total fail, is me trying to pull a hard problem for you. So negative integral 1 over x plus 1 dx. So negative natural log x plus 1. So man, I don't even have to do a bunch. I can go back up here where I did that check mark. I can just squeeze that answer right in here, can't I? 1/3 x cubed minus natural log x plus 1. There we go. That was number 30 out of the book, by the way. Let me see here. What chapter are we in? 6? This is 6.3? I'm looking through some of the answers to see if there's here's the problem we just did. So this is what the solution manual shows you. Talk about leaving some work out, right? You know, this is, well, I guess, yeah, they just didn't show the division. No, they did long division right here. They didn't show you, they didn't tell you, oh, this was long division. Right, because isn't that what we got, x squared plus the remainder of a divisor? Right, they just didn't show that. And then they did the cubic. Let's look at some of these. This is obviously an integral. Oh, we did this one, didn't we? That's the one we just did in class, I believe. Did we get that answer? No, that looks a little different. We had x squared plus 1, didn't we? Yeah, so that was a little different. I'm trying to find something that looks like it had a lot to do. That was pretty clean. I mean, look at this one right here. Can y'all see this one? Can y'all see this okay? Do I need to blow this up? Look at this integral right here. Right? You could start really torturing yourself with this, but if you take the derivative of the bottom right here, you get 5x to the 4th plus 15x squared plus 5, which is exactly this, but you're off by 5. So that's a basic substitution problem. Can you imagine if you tried doing all the partial fractions on that thing, and in the very beginning was a basic U substitution? That they put that as number 34 or 32 in the book. Why? Because they know you've forgotten to do the other stuff first. Always check the other stuff. So they're checking to make sure that you're not going to kill yourself doing something that you don't have to do. What's this? Repeated, irreducible, quadratic. So what do? Yeah, well, looks like they did something a little different here. Go and do this one? That one looks interesting. Let's do it the way, whichever way we want to do it. Let's not necessarily follow theirs. Which one was that? 33. No, it was 33. X minus 3 x squared plus 4x Oh no, 2x plus 4 squared. Do you see a basic substitution? Derivative of this would be what? 2x plus 3. 2x plus 2, sorry. Got 2x plus 2, we needed this. We're off a little bit, right? Can we tweak it to make it match? We could, right? Now, the one I did in class didn't have the squared on it. What does the book kind of tell us we should do here? We have a repeated irreducible quadratic, right? It says that we should do a linear over that quadratic and then plus a linear over that quadratic squared. I kind of already have a linear over that quadratic squared, don't I? You see that? Okay, I already have, that's what I'm getting at, is that this should turn out ax plus b over that quadratic, or I'm just put q, plus cx plus d over that quadratic squared. That's what partial fractions tells us we should do. Well, we already have this, don't we? You see? So why go do this? All that's going to do is create another integral you've got to figure out. Understand? So we're already kind of in the best case scenario right now. So what are some options? Think through this. Make that u and then try and tweak that? Okay, let's see what happens. If u is equal to x squared plus 2x plus 4, the derivative of that is 2x plus 2 dx. I've got to make this thing up here a 2x plus 2. So what do I start with? 2 on the top and bottom out here. New integral is 1/2 integral 2x, I won't mess up this time, minus 6 over x squared plus 2x plus 4 squared dx. What now? I need plus 2, right? So plus 2 minus 2? 1/2 integral 2x plus 2 minus 2, but I still already had up there minus 6 over that. That's going to allow me to split this up right there. The 2x plus 2 over that, right, with the 1/2 in front, will turn into a what? Be careful. This will be what? U sub, but what it'll be 1/2 integral 1 over u squared, right? U squared, not 1 over u, because so the antiderivative will not be natural log. But we'll be able to handle it, won't we? Okay. Now on this one, I've got to put these two together. That's a -8, and then can I take that out of the integral? Okay, so I'm going to just rewrite everything. I have 1/2 integral 2x plus 2 over my x squared plus 2x plus 4 squared dx. Then minus 4 integral 1 over x squared plus 2x plus 4 squared dx. I'm putting a check mark on this one that we can do this with the basic u sub, right? Basic u sub on this. Oh yeah, the minus is from right here. -8, and then bring it out as a -4. We good? Okay. How are we going to handle this? Before, if that squared wasn't there, what did we do? We completed the square and then did arctan, right? But that squared is going to, you cannot use the arctan formula here. So, but should we still try and complete the square? See where it leads us? Let's just try it, okay? I'm doing this problem, taking it to a new page. Integral 1 over x squared plus 2x plus 4 squared dx. Completing the square, I do not have to factor out a 1, do I? I mean, factor out anything because I have a 1. So I will take half of 2, which is 1, and I'll add and subtract it. Do you agree we have that? So I completed the square from here to here without showing the steps. But do you agree that that's the correct completing of the square? Take half of 2, it's 1, square it, it's 1, add and subtract 1. You'll get this, the first 3 terms, and then when you subtract 1 from 4, you get that. Now what I'm going to do, I'm going to convert this over for a second. Do you agree that this has the same format as this? Like if I did a basic u substitution here, where u is x plus 1, right? U is x plus 1, then du would be dx, and everything works out. It's a nice conversion that way, right? Now what? It's not arctan, right? Because it's squared. You mean go to 2 separate ones? Yes, but then you can't say arctan for each one, because remember, that's can't undo the product. I'm going to give you a hint, but it's probably going to give it away. Could you handle that? How would you do a problem like that? That's not this, but if I gave you this problem, what technique would you use for this? Trig substitution. Trigonometric substitution is what you would use for this. Why? Because the form you have is the square root of something squared plus a constant squared, right? That's a trig subproblem. But that's not what we have, right? But we do have it. If you raise it to the 4th power, that is exactly what we have, isn't it? If you take a square root and raise it to the 4th power, that's the same as this. This is a hidden trig subproblem right here. So what is the substitution that we make when you have, well, in our formulas that we used x, didn't we? If we had x squared plus a squared, what was the substitution? X squared plus a squared. We said x was equal to, I know we did it. I was here. Oh, holy crap, look at that. I went right to the page. If we have something like this, a constant squared plus our variable squared, we make the substitution that it's our variable, which in our case is u, isn't it? U will be equal to a, which a for us is what? Square root of 3 tangent theta. That's what I'm going to do. So in this right here, I have the form of u squared plus a squared. Therefore, my substitution is u is equal to a tangent theta, which is u is equal to square root of 3 tangent theta. Everyone understands root 3 because that's a squared, right? 3 is a squared. Now derivative. Derivative of u is root 3 secant squared theta d theta. And what does our formula tell us that the square root of u squared plus 3 is going to turn into? I'm going back again. I'm looking at this right here. If we have this form, that square root thing is going to be a secant theta, which again would be root 3 secant theta. Now, rewrite that integral with your substitution. Integral 1 over what's the square root of u squared plus 3? It's this, right? It's root 3 secant theta, but then to the 4th power, right? That's this. Then what's du? Root 3 secant squared theta, d theta. What's root 3 to the 4th power? Root 3 times root 3 is 3, and then do it again, 3 and 3. So it's 9, right? It's a 9. And then I have a root 3 up top. So can I just pull a root 3 over 9 outside? Okay. Now this is going to become secant to the 4th down here, and secant squared up there. Right? Secant squared on top, secant to the 4th. So 2 of them cancel, so all I'm left with is what on the bottom? Secant squared. 1 over secant squared is cosine squared. So this is really just cosine squared theta d theta. And how do we solve? Man, what a problem. This is a good problem. How do we do a problem like this? Yeah, the power reduce, right? 1/2. So we can handle this now? And then we have to get all our thetas back to u's, and then all our u's back to x's. So let me go back to that solution. Maybe that solution will make more sense to us now. Let's see how much of the work they show here. Well, hey, there it is right here. Right there, right there. Yep, it's in here. And then from here, they kind of show it in here. Why is there a sine theta, cosine theta in here? Yeah, because when you break this down, it's going to give you 1/2 plus 1/2 cosine 2 theta, right? Right, doubles it. I don't think I want to take this the rest of the way, because I mean at this point we've done that. Just go look in your notes. We've done that. It's just a matter of substituting everything back in. Right? What do y'all think? It's a good problem. That's why it's number 33. You had a combination of a lot of stuff here. All right. So what I suggest you do is take a look. Now this section is completely opened up as far as homework. You should do at least the first 33 odd ones, 1 through 33 odd, but you should also look at the evens. That's hours and hours of work. So see what you can do. I wanted to show y'all something normally wouldn't show you. Well, what the heck? YouTube. Oh, this right here. Now, I want to see if I can get the audio to work here. I don't know if I'll be able to get the audio to work. I mean, you might hear it, so check this out. You know what? By the way, I'm going to pause